Hey everyone, welcome back. Let's talk about another medium problem on Leetcode today. Combination sum, Leetcode 39. This problem is part of Blind 75, a curated list of essential coding interview questions. You can find the full list linked in the description below. Be sure to check it out. Now to the problem. In this problem, we are given an array of distinct integers called candidates and a target integer called target, and we have to return a list of all unique combinations of candidates where the chosen numbers sum to target, and we may return the combinations in any order. The same number may be chosen from candidates an unlimited number of times. For example, here in example 1, for the given candidates and target equal to 7, we choose 2 multiple times. Similarly, in example 2, for given candidates and target equal to 8, we again choose 2 and 3 multiple times in different combinations. And two combinations are unique if the frequency of at least one of the chosen numbers is different. That is, the order of the numbers in the combination don't matter. And the test cases are generated such that the number of unique combinations that sum up to target is less than 150 combinations for the given input. Then in example 1, for the given candidates array and target equal to 7, we have two combinations possible, which are 2 to 3 and 7, which sum up to target. Note that 2 is used multiple times, and the combination like 232 or 322 are a valid combination, but they are duplicate of 223 because the two combinations are unique if the frequency of at least one of the chosen numbers from candidates is different. Similarly, in example 2, for the given candidates and target equal to 8, the output will be following because all of these combinations are unique and sum up to 8. Now, in terms of solution, we can use backtracking to explore all possible choices, but stop the exploration as soon as certain constraints are violated, such as when the sum of the combination exceeds the target. Now, the naive way to perform the DFS would be considering all choices. So we start with the empty combination and draw the decisions in the decision tree from the available values that are 2, 3, 6 and 7. As we traverse each path, we keep track of the running sum along the way, which will be 2, 3, 6 and 7 for the respective paths. Now, since the sum here is 2, which is below the target 7, we can go further down, generating the choices 2, 3, 6 and 7. Note that we are forming combinations where repetition of numbers is allowed. Hence, we can choose 2 again. This is different from permutations, where we would have only considered 3, 6 and 7 at this point. So now our combinations become 2, 2, 2, 3, 2, 6 and 2, 7. And now here the sum is 4, which is below target. So we go down further and choose from 2, 3, 6 and 7. And here now the sum is 6, which is below target. So we will try to go down further again with 4 choices. And now the sum here, for example 8, is more than target. So we backtrack. Similarly, we will backtrack from these other paths as well, as the sum of the combinations is more than target. Now coming to this combination, the sum is equal to target. So this is a valid combination. But from here on, again the sum of the combinations is greater than target. So we will backtrack from these paths and come to this point. Now, continuing further from this path, again we will have 4 choices with combinations as 232, 233 and so on. And note that sum of this combination is also equal to target. So this is also a valid one. But it is a duplicate of this one, as the chosen numbers 2 and 3 in both the combinations have same frequency and order does not matter. Similarly, if we continue with this 3, eventually we may have a combination like 3 to 2, which is again a valid combination but duplicate of 2 to 3. And this happens because the naive approach does not impose any order and allows unrestricted branching. So how can we ensure uniqueness in the combinations generated? To do this, we address the main problem in the previous approach, which was allowing numbers to appear in any order. For example, 232 versus 223. The fix is to impose an order constraint by restricting which candidates can be added at each level of recursion. So at any current position in tree, we should only consider the current number or numbers appearing after it. This ensures the numbers are explored in the order they appear in the candidates, so duplicate permutations are avoided. Now, again we start backtracking by iterating over the candidates using an iterator I, initially at index 0, pointing to number 2. But we now have two decisions to make, which is to include 2 or not include it. So if we include 2, we stay at the same position and we don't move the I pointer forward because we can reuse the same element. Now, the sum of the combination is 2, which is less than target of 7. Hence, we go deeper and again we make two choices, whether to include 2 or exclude it. Note that this process ensures that the left path is distinct from the right, and this guarantees unique combinations. On the right side, however, when we exclude 2, we will move the I pointer forward and consider the next value, which is 3. And at this stage, we repeat the same process for 3. That is, either we can include 3 or exclude it. Now let's focus on the left side a bit. At this point, the sum of the current combination, that is 2, 2, is 4, which is below the target. So we go deeper and again we have two paths where we include 2 or exclude it. And for this combination, the sum is 6, which is less than target. So we go deeper and again we have two choices, whether to include 2 or exclude it. And now on the left, combination sum is 8, which is greater than target. So we backtrack and come to this path and exclude 2, and hence we move I forward and again ask the same question, whether to include candidate at I, that is 3, or exclude it. But again we would have to backtrack because the sum 9 is greater than target, and similarly for rest of the numbers as well, like 6 and 7. So we backtrack to 2, 2. So now because we didn't include 2 here, we will move I pointer forward again. And again we will have two choices, whether to include 3 or exclude it. And this time on the left, we will get the combination sum as 7, which is equal to target. So we will add it to our answer. Note that how all the 2's have come together before 3, which avoids duplicate combinations. Similarly, we will go through the rest of the tree here and here. Now on the right side, again we will have two choices, whether to include a 3 and get 6 or exclude it, and so on. And here if we exclude 3, we will move the I pointer forward. And again we will have two choices, whether to include 6 or exclude it. And then again we will have the remaining tree. Similarly, if we exclude 6, again we will move the I pointer forward. And again we will have two choices, whether to include 7 or exclude it. And now if you look at this point, this combination of 7 matches directly with the target. So this is also a valid one. Hence, we add it to our answer. And here now I is equal to 3. So we have reached another base case, as now we have come to the end of the candidates array. Hence, we don't have any more candidates to choose from. Now this process efficiently generates all unique combinations by avoiding duplicates efficiently, thanks to the ordering and proper backtracking logic. Here is a more visually appealing recursion tree created using Xcali Draw in case you prefer it. Now, the time complexity of this approach is O of n to the power of d, where n is the size of the candidates and d is depth of the tree. And the reason for this is the depth of the recursion is proportional to target by minimum of the candidate. For example, here for target equal to 7 and minimum candidate equal to 2, depth of the recursion will be at least 4 with combination as 2, 2, 2, 2. And then for each label, we may have at most n branches, where n is the size of the candidates. Hence, the overall time complexity will be O of n to the power of d. Of course, pruning helps reduce the number of paths explored, but does not change the exponential growth, especially in the worst case. And in terms of space complexity, it will be O of d, which is the space required for the recursion call stack. Here is a quick code walkthrough of the algorithm we just talked about, with Java code on left and Python on right. First, we initialize an empty list called answer to store the resulting combinations. Then we define the recursive backtracking function, which takes in the candidates and the answer array, along with the index I for the current candidate, current sum of the numbers in the combination, and the current combination as the parameters. Inside the backtracking function, First, we check for the base cases, which are if current sum is equal to target, we add a copy of the current combination to the answer list and return. Otherwise, if current sum exceeds the target or index I reaches the end of the candidates list, we will return from this function and stop the recursion. And now we have two choices, either to include the candidate at the current index or exclude it. First, let's look at the inclusion case. So we add the current number to the combination and recursively call the backtrack function with the current index I because the repetition of the same number is allowed, along with updated current sum of the combination and answer, and backtrack by removing the last added element from the combination. Now let's look at the exclusion case, where we exclude the element at the current index and recursively call the backtracking function with the next index I plus 1 and the original current sum along with the rest of the parameters. And we start the recursion with index 0 with initial sum equal to 0 and an empty combination. And once the backtracking function completes, we will return the list containing all valid combinations. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.